Okay. So I have I I'm giving the detailed proof of the new Liouville theorem, but I think it's easier to first present the moving sphere procedure, and then I will address the new ingredients needed. So last time I went through a proof of Caffarelli, Gidas, and Sprague's Liouville theorem, and I think I gave the proof modular 2 calculus lemma. So I think I described the one calculus lemma, how the proof goes, without writing down all the details. I think today, I think maybe it's better. I'll just present this uh, calculus lemma. So I will first just do two calculus lemma. So, so the I will follow I will follow a proof. I will follow a proof. Um, this is on a paper. So I will then just look at page 176. And its proof is like one page. So I will do lemma 5.7 there. So, so for n greater or equal to 1 in Rn, and the new a real number. So let f, which goes from Rn to minus infinity to infinity, satisfying okay. So let's just give a proof of this. So, so for all y, z in Rn, y not equal to z, will prove f of z less than f of y. Then done. Because I can switch the role of z and y. So then f of y will be less or equal to f of z, then they are equal. So I draw y here, I draw z here, and then we have a straight line determined by them. Okay. So then I will put an x here. So how to determine x? For b bigger than 1, we let x equal to y plus b z minus y. Okay. So it is here. Yeah, you see, okay, it is on this side. You see, it's quite clear. It's here. So put it this way. Oh, y and z. Y minus x minus y is equal to b z minus y. So x minus y and z minus y. So they are in the same. As you can see, they should be here. Yeah. So then we let lambda to be equal to z minus x, y minus x. So this is exactly the inversion radius. So when you make a inversion, oh, I draw more. So when this radius, so you see z minus x times z x minus y is equal to lambda square. If this radius is lambda, then this z I x minus y should be bigger than lambda. So y minus x is bigger than that. Okay. So z. So you see this z is exactly equal to x plus lambda square, y minus x, y minus x squared. So this should be right. Yeah, something like this. So this is how you link. So these are fixed. So okay. So then you will see lambda. Your relation will give you y minus x nu f of z less or equal than y. Right. So now you see, so you see y and z are fixed, b is fixed, then b x equal to x determined by b, lambda is determined by b. So now here I send b to plus infinity. You will see for when then this x will go this way. When you send b to infinity, you see this b, this goes to infinity, so x will go this way. When x goes this way, so you see lambda over y minus x will be equal to root z minus x divided by y minus x. So z and y are fixed. So this will go to 1 as b goes to infinity. Because when b goes to infinity, this x will also goes to infinity. Goes exactly this way. So then you send b to infinity in here. So lambda, so this part will go to 1. So you will have f of z less or equal to f of y. This is exactly like what I draw last time. I make this circle get bigger, bigger, and so on. So we are going to see this. So this is what I described last time and in formula. Okay. So the next calculus lemma will be like this. It's still in the same as I described here. So as here, it's lemma 5.78 there. So for n greater or equal than 1, nu belongs to R. I think we use the nu equal to n minus 2. So, and f is a continuous function. Suppose that for every x in Rn, there exists a finite lambda of x, positive, such that if you take nu equal to n minus 2, that is the Kelvin transform with that radius is equal to f of y for all y belongs to Rn minus x. This is what we reached when we're doing this moving sphere. Then the conclusion is for some a greater or equal than 0, the positive, and the x bar in Rn, this function f must be identically equal to plus or minus, depending on the sign of your function. It will be either plus or minus. You have this. And this is give the second calculus lemma we used. So here, this equal f here is C0 is good enough. So in this place, there's a proof for f is C0. So I will now just give a proof. So I will just give a proof for a proof when f is C1 instead of C0. You need to do some work if f is C1, C0. Okay, so if f is C1, we give a proof. So this proof you can find, so this proof you can find in a paper with Lei Zhang in Journal of so this proof This proof is on page 80, lemma 1, yeah, there, yeah. So, and I will write the proof. So in fact, last time, the proof, you can find the proof of this Caffrelli-Gita-Sprague, that Liouville theorem proof. It is in, you can find in this paper, and you can find on page, okay, on page 36 to, this is what I described last time, 39. So let's let's prove this now. So, so I let B dot to be defined by limit y goes to infinity, y to the new f of y, that will be equal to, so what we do is we multiply this, we multiply this by y to the new, by y to the new. You multiply this by y to the new. So when you multiply that, this hits that, you send y to infinity, will go to 1. So therefore, the right-hand side, you have y to this will go to 1, this will go to 0. So therefore, you will see from there, so this has a limit, and this limit is equal to this, f of x. And this is true for all x. So in particular, this, yeah, it satisfies this. So if the b equal to 0, then f is identically equal to 0. So in the, yeah, so in the statement, this a will be 0. You take a equal to 0, so f equal to 0. Otherwise, if b is not equal to 0, then f does not change sign. Because you see from here, this is always equal to the sign here. So it doesn't change sign. So it's either positive or negative. So without loss of generality, b is positive and is equal to 1. If it's positive, I can divide f by b. So the new f will still satisfy this, because this is linear in f. So you take b equal to 1. Otherwise, you take b equal to -1, the proof is the same. So now we know that f is positive. So you look at this expression, you take and look at here, you take large Y. If you take large Y, you see you can make an expansion. This goes to zero, but you can make an expansion. And you can write it properly. And this one, this will go to zero. So you can make Taylor expansion and so on. So what you can write is, so making a Taylor expansion for large Y. So you can make a Taylor expansion to the left-hand side of this expression to here. You just, then you will see that f of y is equal to lambda of x, y minus x to the new f of x plus df dyi at x, lambda of x squared, yi minus xi, y minus x squared, plus little o, 1 over y, for fixed x, for every x. So for every x, you can, for example, for every x, so here you have y large, you just make Taylor expansion. So this one, I just put it there. Yeah, I put it like this. Well, you can also say, I can also take x equal to 0, for example. I'm going to have f of y equal to lambda of 0, y to the new, and f of 0 plus df dyi at 0, lambda of 0 square, yi, and y square plus little o. Okay. So you have two expressions. They're the same. They're the same. So now what you can do is you can just expand. You can always expand, write everything or this in terms of 1 over y. For example, if you have 1 over y minus x, you can always write it as y, and y over y minus x over y. So this is a unit size, and this is little o. You make Taylor expansion and so on. You can always write those things in terms of this 1 over y and so on. Then you compare coefficients. When you compare coefficients, you will see these two expressions, you write them the same way. So you will see, to compare coefficients, you will see f of x minus 1 minus 2 over nu df dyi at x should be equal to f of 0 minus 1 minus 2 over nu df dyi at 0 minus nu xi. This is what you are going to see. You just compare coefficients, the leading term, yeah, high order term is, so it's just like comparing a polynomial. If two polynomials are the same, corresponding coefficients should be the same. So it's the same here. So this is for every x. So what is that? So you see, this means the derivative. So this is really the derivative of minus 2 nu d dyi, okay, and the minus nu over 2. So this gives you the left-hand side at x is equal to a linear function, okay, with a constant with not a constant, it's a this this yeah minus that. You can say this is AI, yeah, alpha gamma I minus xi or something, new xi. So if partial the grid is a linear function, so this before taking derivative is a quadratic function because this is linear. This is equal to that. This is equal to this. So the gradient of that is I. So that means it's a quadratic function. What you have is a quadratic function. This function has to be a quadratic function. So a quadratic function can always be written as y minus x bar square plus a d. You can always write like that, quadratic function. And I, I, okay. I should have a as well. Oh, because that a I take it as 0. B is equal to 1, so that a is being determined. So if you look at here, you see this d has to be positive. So this d, otherwise, this function will have a 0. But f is positive C1, f to the negative power cannot have 0. So this implied d should be positive since f of y positive is C1. Okay, so d has to be positive. So now you have proved that f of y must be equal to 1 over y minus x bar square plus d by nu over 2. So you don't see the a there because when we do without loss of generality, we assume capital B is equal to 1. We already normalize that constant to be 1. So this settles the elementary lemma, second elementary lemma for fd1. Okay. So for fc0, one can read that paper. Okay. But in this business, we didn't use fc0 even. For us, we have higher regularity. So now when we now this gave a complete proof of this Caffrelli-Gidasen-Sprague's Liouville type theorem. So when we described earlier for the more general Liouville type theorem for the proof, we need a few ingredients as we so one ingredient we used is a removable singularity result. For example, if I have a function u, if I know lambda of au belongs to, say, gamma bar in a punctured ball in viscosity sense, and this gamma has enough positivity. So this should not belong to gamma bar. So namely, this thing somehow this lambda star is somewhere here. So and now I write it as equilibrium. So in that case, we can prove that lambda of AU belongs to gamma bar in B1. So, so this positivity of this conformal Hessian allows removability of isolated singularities for super solutions. So this is a super solution, you can go over that. And the same as you have it, if you have f of lambda of AU, greater or equal than 1, for example, in B1 minus 0. And again, you have lambda of AU belongs to gamma bar in B1 minus here. And this lambda star is not in gamma bar. So the lambda star by definition is 1 minus, minus, minus. So in that case, we can extend the super solution across. Okay. So this maybe next time I will give some di discussion on that. So this is one ingredient, important ingredient. This is very important ingredient in proving that general Liouville type theorem. And this removability, this positivity is also necessary for this removability. So after that, we also need a statement, a strong maximum principle statement. Namely, we need the following. So this is one ingredient. Second ingredient one needs is that if you have a super solution U, for example, if you have super solution greater or equal than 1 in B1, and you have a subsolution in B1, and the U is greater or equal than V on boundary on in B1. So let's just say, let's make life easier. I will just say, okay, I will assume U is actually bigger than V in B1 minus 0. Here, I assume also UV is C2. But I assume U is only lower semi-continuous on B1. So we will still be able to prove that U and V is U is bigger than V at 0. So we still have U0 is bigger than V0. So this is strong maximum principle. We are saying strong maximum. The point is one is C2, one is lower semi-continuous. You can still do that. So I think I will, and this result, actually, which we will need, we need. So actually, such result for elliptic operator, second order, and was proved by Caffarelli and myself and Nuremberg. In 2013. So that's for uniform. That we look at the operator. So the proof can be adapted to prove our setting. So I think maybe I will discuss such this ingredient today. I will follow that paper with Caffarelli and Nuremberg. Okay. Because the statement is uh, is more common in a way. Yeah. So I will do this. So I will say, so this is in CPAM 2013, I think. Let me find it. Yes, 2013. Okay. So I will present a couple of pages there. It goes from 1 to 25 to 129. So, but I streamline some part of proof a little bit. Okay. So this is just about maximum principle and strong maximum principle. So, but the point is one C2 and one semi-continuous. So then the usual one will still go through. So I will take, so this is self-contained, this part. So omega, let's take Rn open bounded. Okay. So we'll consider two functions. U is lower semi-continuous in omega bar. Well, V is C2 omega intersects continuous omega bar. I always look at this situation. And I will assume this F, there is a second order elliptic operator. So, and this F is assumed to be elliptic. F Mij X SPM. So I call this SPM. So cosine I, cosine J is positive for any cosine not equal to 0. Cosine is in Rn. So this is the positivity. So this is a n by n symmetric matrix. So actually, I don't need for all. I actually only need but this is for all x s p m. I think let me see. Yes, I need for all of that. There's a fixed direction, but of course ellipticity will give you this. But for the argument to work, you only need to have a special fixed direction, but should be independent of all the arguments, this fixed direction. Okay. So now the theorem is, so this is maximum principle. So assume u greater or equal than v on boundary omega, and assume also inf u is bigger than minus infinity. Yeah. So then u greater or equal than v in omega, provided this fs x spm is less or equal to 0 for all the arguments. So if two solutions are C2, so this is very standard. Yeah. So I want to go through this proof to get familiar with this viscosity solution sense, how to do that. Yeah. So let's give the proof. So we may assume Fm11 positive for all its arguments. Thus here you rotate, this psi can be taken as 1, 0, 0. Yeah. So this psi, you take it as 1, 0, 0. Yeah. You just rotate that, you will have this. So we argue by contradiction. So we argue by contradiction. So suppose not. So if then that means, so we know that the inf of u on omega will be positive, negative. So because you without, so we'll do at v equal to 0. So I should wait a minute. Yeah, I should set it up first. So I should say that, so we may assume that, so we can look at this new f. So we look at f spm minus f of x, v of x, gradient v of x, Hessian v of x. So you look at your new f. If you work with that, you will see v equal to 0 is a solution. So then you just look at a new one. So then you will see that we may assume that your u, this is for your new one, it is less or equal to 0 equal to f of x 0, 0, and 0 in viscosity sense. So namely, your v is actually identically equal to 0 in some sense. Yeah. And then you know that u greater or equal than 0 on boundary omega, and you want to prove that u is greater or equal than 0 in omega. Of course, you are still carrying this condition, provided that condition. The only thing is you take that v to be 0. Then we go like this. So, yeah. So suppose not, then the inf is less than 0. So you want to get a contradiction. And this is omega. So we may assume, without loss of generality, let's say that this u0 is achieved. The minimum is achieved at the origin. It's just there is a minimum point. You make a translation, you can assume, you call it 0. So, and you can give this value minus k. K is positive. K is positive now. Give some. Okay. Now we take the x1 direction, and we may, let's call maximum of x1 in your domain is equal to minus r plus 1. So let's just, we can do that. Just give, yeah. So meaning that I think here is minus r, and here is minus r plus 1. So the inf, I want it to be the inf. Yeah, inf. Okay. So now we use a comparison function. So these are, yeah, okay. So you see that h of 0 is minus k, because when we put 0, this, oh, I should have a k. I should have a k here. So x1 is 0. Hmm? I think I forgot a k here. I should have a k here. So h of 0 is minus k. So because when we put x equal to 0, the last two terms cancel, you have this. You also know that h should be less than 0 on boundary omega. Because on the boundary omega, x plus r, uh, wait. So first, so this is this function is monotonic decreasing in x1 because this is x1, yeah. So it's monotone decreasing. If you look at x1, so when it's equal to 0, so h is minus k here. So h is decreasing. So after when it goes up, it should be go down. So of course it's more negative. So then here is minus r plus 1. Minus r is here. So this x1 is always greater or equal than this number. That means if x1 equal to minus, if x1 equal to, when x1 equal to minus r plus 1, the last term will be k e minus lambda minus lambda minus k e to the minus lambda r minus k. Yeah, so this should be negative still because this is quite tiny. All these are tiny when lambda is large. So this is still taking over because lambda is very large. So it's still negative. So everything is negative. So this is true. Yeah, yes. So u is greater than 0. And here h and u touches. So h of 0 touches. The picture of u will be like this. So your h is like this. If this is the boundary, h is negative, but u will be hitting here, and u is positive on the boundary, not negative. So you can move this h down because this can be like this, can be like inside this u can be like this. It's possible. That's possible. So if you move down h and move up, so it will hit. It will hit here. So you move down this graph of h and move up, you will see that you will be having h minus c0, c0 greater or equal than 0. So they touches at ux bar. So I'm sort of writing this X bar. You move it down and go up, you will touch it. So then the graph touches there, okay, and H bar has to be inside because on the boundary you don't have touching, you will touch inside. So then you have H minus C0 greater or equal than U and equal to that at X bar. Okay, so if you compute, so then you know by the definition of viscosity solution sense, you know that F of X bar H X bar minus C0 gradient H X bar Hessian H X bar, they should be less or equal than 0. Okay, this is by the viscosity solution, meaning H minus of this touches U from below, then by U satisfying this in viscosity sense, so the comparison function H minus C0 evaluated there should be less or equal to 0. So now this is actually greater or equal than F of X bar, H of X bar, gradient H X bar, Hessian H X bar. The reason is this Fs is less or equal than 0. So therefore, this is minus C0 is negative, the value is bigger. So therefore, you have F of X bar, H of X bar, gradient H X bar, Hessian H X bar should be less or equal than 0. Okay. But if you look at all this H, if you calculate HI, you will get minus K lambda delta I 1 e to the minus lambda x1 plus r. Xij is going to be K lambda square delta I1 delta J1 and you know that x1 plus r, because the inf is minus r plus 1, so x1 plus r is always greater or equal than 1 in omega. So this is greater or equal than 1. You have exponential minus lambda. If you take lambda very large, everything will be quite tiny. So therefore, all the arguments remains bounded. So you know this F M11 in all these arguments will be having a bound. Okay, it's FM11 will be positive, have a positive lower bound, bigger than A11 and bigger than a positive constant because they stay in a compact set and it's positive. So it's bigger than A positive. It's 6. Yeah. So here, because F X bar 0, 0, 0 is equal to 0, so this and that you use mean value theorem, you will see that Fij m. So you will see that this you will see M11 multiply H11 plus BI HI plus CH. You just use the intermediate value theorem. So you will see that 0 is greater or equal than that, because 0 is greater or equal than this. You put it in H11, you will carry a lambda square H11. So you are going to see this is FM11, and you see K lambda square e to the minus lambda x1 plus r. And the next one you will see is minus K lambda B1 e to the minus lambda x1 plus r, and plus C H something. CH minus, wait a minute. H minus H0. But the C should be less or equal than 0. C is less or equal than 0. To organize here a little bit. Okay, one is supposed to get something like this. One is supposed to get something like this. Your FM11 lambda square minus lambda B1 plus C. So I messed up here a little bit. So then you make lambda very, very large. This will be bigger than 0, contradiction. So this is kind of a standard argument, but you make it, you actually use only the one is with semi-continuous in weak sense. So next time I will write a proof for the strong maximum principle. One is semi-continuous, one is C2. Yeah. So any questions?
Any questions? Any questions online?
Yannick, can you explain a little bit the first lemma, where not the second lemma about the classification, where you use C1? Can you give some idea about the case C0?
Okay. So if it's C0, yes, I may need to prepare a little bit in a way, because it's not very, I cannot finish in 5 minutes. So what I can do is I can present next time maybe.
Sure, yes. Sure, Professor Lee. Yeah, no problem.
Yeah.
Okay, any other questions? Any questions online? Okay, so no other questions. So let's thank the speaker.
Thank you.
Okay, thank you, Professor Yannick.